Now we're going to be looking at inequalities and systems of inequalities in two variables. So the inequalities we were looking at before were just in one variable. All those absolute values. They were just in one variable and in one axis. These are going to be in two axes. So we have our y and our x-axis. But it's going to be very similar. We're going to use a lot of the ideas from inequalities. Like, right, we can't forget that if you multiply or divide by a negative, this inequality needs to switch. But we're going to also add looking at linear equations, how to graph them, and we're going to particularly use how to graph using slope-intercept form. So let's just start with an example. So to be able to graph this linear inequality, I want to isolate my y value. To do this, I need to move my x over to the other side. So we're going to do that by subtracting 3x on both sides of the inequality. And this doesn't switch the inequality because we aren't multiplying or dividing by a negative. That cancels on the left hand side. Leaves us with negative 2y is smaller than, and I'm going to write negative 3x plus 6 because I want to get it into that y equals mx plus b form. So I want the x to be first. Now I'm going to divide both sides by this negative 2. Now when you divide by a negative 2, this doesn't cancel, it just simplifies to 1. But it does leave us with y. But now we have to make sure we switch our inequality because we divided by a negative. And when you, let me make a quick note here. When you divide one denominator by one term in the denominator and multiple terms in the numerator, you can actually separate the fractions. So that's going to look like this. I'm going to do it right here, an example of this. You're allowed to split them. And it's just adding fractions in reverse. Because when you add fractions, you need the same denominator. And when they're the same, you can combine them into one. So that means I'm going to just divide these two together and then these two together. And negative divided by negative is positive. It's going to leave us with 3 over 2x plus, and then 6 divided by negative 2 is going to leave us with a negative 3. Now with slope-intercept form, we have to identify the y-intercept, which is going to be, let's write it down. The y-intercept is 0, negative 3, and my slope is 3 over 2. So 0, negative 3 means that we're not going to go anywhere left or right on the x, but we're going to go down 3. So it's going to be right here. And then we're going to find our next point by going up 3 and right 2. So 1, 2, 3, and then 1, 2. So here's my point, and I have my line now. But something that's going to be different than, and we're going to adopt from when we looked at linear inequalities, was when we didn't have that equal to sign, we had an open circle for our 4. So in this case, instead of having an open circle, we're going to have a dashed line. So first let me make the line, and then I'm just going to make small little erases to give the dashed line effect. Now, before, when it was equal to, that's why it was just a solid line. But here it's saying any y or x values you choose are going to give you, as long as you satisfy this inequality, you're okay. Now, any point that's on this line used to be a solution. But if I take any of these points and plug them into this linear inequality, we're going to get a false statement, because these two numbers, any number that's on this line, are going to end up with the same number on each side. And it's not going to be bigger. Both sides are going to be equal to each other, because we graphed it as if it was an equation, not an inequality. So the inequality gave us the dashed lines. But where are the ordered pairs that satisfy this solution? So this is where I look at the variable that's oscillated, which is y. So that means I'm going to look at my y-axis, and I'm looking for the y values that are, remember, this open side is the larger side. So point here, where are the points that are larger on the y-axis? Are they above or are they below? And those points are above this y-intercept. So that tells me that this side of my line is my solution. And I'm just going to shade this in like this. It's not going to be perfect, but hopefully, again, you don't want to cross that line. But any point that's on this side of the line satisfies this inequality. And you can check that by just choosing any ordered pair on this point. For example, let me try this point right here. I'll try a different color. We're going to try this point right here, which this point is -2, 0. So I'm going to plug it into this inequality, or you can plug it into your original one. You're still going to get a true statement. So your x is -2. So I'll plug it into the original to just show you that everything works. Minus -2 times 0 for the y has to be less than 6. So -2 times 0 is 0, and 3 times -2 gives me -6, and that is smaller than +6. So that would be one way of verifying, but if we just use the inequality symbol, we know which side to shade. So let's look at another example. We're going to do the same thing, just going a little quicker now. Let's subtract 3x on both sides. That leaves me with -y is smaller than -3x plus 3. All I did was just change the order to have it in that slope-intercept form. And once again, I'm going to divide by -1. I'm going to do that to each term. I already did the splitting, if you notice here. Last time I divided to the entire right-hand side, which is what's happening. But to save some time, I split the terms already. And that's going to leave me with y. And I have to switch the inequality is bigger than 3x minus 3. Once again, the y-intercept is 0, -3. And my slope is going to be 3/1. So have the same y-intercept, but the slope is different. So I'm going to go up 3 this time and right 1. So that's going to give me a point right here. And once again, there's no equal to here. So instead of a solid line, we're going to have a dashed or dotted line, however you want to call it. And I'm just going to quickly just erase to give it that dashed line effect. And same as before. It's asking for the y value to be bigger. I go to my y, because the y is isolated. I'm not going to my x-intercept. If the x was isolated, then I would go to the x and determine which side is bigger and smaller. But on the y, the ones that are bigger are above. So once again, my solution is here. And I just shade in my solution. Now, we can be careful because this looks like the type of inequalities we did before, where it was just one variable, but we're taking this one, it's only one variable, but we're doing it on a XY axis. Now, if you remember from before, what happens when X is equal to a constant? We have it here. Note the equation, that's supposed to say equation of all vertical lines is when X is equal to a constant and the slope is undefined. For horizontal lines, the equation of all horizontal lines is when Y is equal to a constant and the slope is 0. So that's true for any type of line, even if it's an inequality, if you're putting it on a coordinate system like this. And if we see the equal to, that tells me I'm going to have a solid line at positive 1. So I'm just going to draw my vertical line at positive 1. Of course, this line goes up and down forever. I know I'm not putting the arrows in, but these lines do go in each direction forever. Now, since this has to do with X, I'm going to go to my X-intercept, which is the points where it crosses my X-axis. And it says that it needs to be smaller. So where are the numbers smaller on the X-axis? Remember, they're bigger on the right, smaller on the left. So then the side I'm going to shade is this left-hand side. And there is my solution. We can even add non-linear inequalities here. Looking at this y squared. Now, for the sake of time, hopefully you remembered when you had x equal to y squared, it was very similar to y equals x squared, which is a parabola, but now it's a sideways parabola that it goes through the origin, has this point at 1, 1, and 1 and negative 1. So I'm going to sketch that quick graph here. And since it's not equal to, again, I'm going to have to make a dotted line. So that's roughly the graph. And then I'm just erasing. But again, I go to the x-axis because you can either see if ordered pairs here satisfy this inequality or ordered pairs on this side, because this just sort of splits this coordinate system. You can choose ordered pairs and test them, or I go to the variable that's isolated, which is my x, and I'm looking for those that are larger. So the ones that are larger are on the right. So that tells me that I'm going to shade this inner part of this graph. So it's going to look something like this. It's going to re-graph it. Try and get it nice and clean. And of course, everything in this direction continues and it keeps shading. We just sort of stop here. But that's the graph. Should probably shift this over a little bit to give us some room. There's our graph. And here's another example of a non-linear one. Luckily, this is already our y is isolated. Remember, when it's absolute value, that means we're dealing with a v. And let's not forget these simple transformations that we talked about. Everything inside happens opposite of what you think. So this 2 is actually going to move it. And if you remember the parent function, it started right at the origin. Right? It would look something like this. But that 2 moves it twice to the left. And it would be here now. And that negative 1 moves it down 1. And since it says it's equal to, this is what the graph is roughly. And then, once again, we go to the y part. The y-axis. Since our y is isolated, I go to the y-axis. I look at my y-intercept, and it's asking for the ones that are equal to. That's what's a solid line. And it's asking for those that are smaller. And I know my y values at this point are smaller below. So that tells me I'm going to sketch this part of the graph. And I'm shading it. And at any moment, you can always pause the video. You can try the example before I do it and see if you get it right. Then we jump into the system portion of these inequalities, where we're actually graphing two problems in one. So here, we graphed this one already. So it was our sideways parabola. So I'm just going to come here and copy this. I'm going to paste it on this side. So we save some time there. Same graph, same problem. All right, look, x is greater than y squared, x is greater than y squared. And if you look here, this one is the same as the one we did up top, where we have it isolated, and then we have it graphed. So I'm just going to copy this one as well. Just going to hit copy. It's not perfect, but oh, it should be here. There we go. Right, because the y-intercept was here, and then the next point was there. And if you notice, what is the solution to this? It is where it's essentially the area that satisfies both of these two. And that area is in here. This little space is my main solution in here. I'll keep highlighting it to make it more noticeable. Not including the dash lines, but just that little space in here. And you can find an ordered pair. Try either. That would be 1/2 and 0. And you'd notice that that would satisfy both of these two inequalities. And we have more. Once again, we see the absolute value. The y is isolated. The absolute value we know makes a v. We know this negative brings that v down. So that graph is going to look something like this. So here, whoops. Try to sketch it. Here's our graph. But this time, before we had under, but our y says it's looking for the numbers that are bigger. So it's solid line because of the equal to. But remember, the y values that are bigger are above. So I'm going to shade this portion of this inequality. Here. Here. And there we go. And now this, once again, it is one of those transformations where the x is squared, so I know I'm dealing with a parabola. But this negative, I know, makes a parabola reflect downward. So it would have started like this, curling up. The negative curls it down. And then this 2 makes it shift up. So it's going to look, and since it's not equal to, it needs to be a dashed line. So I'm going to do that by just putting it where it goes. And I'm going to move it to the side so I can make my dashed line. Here it is. And this y wants it to be smaller. So those are all the points that are. I go to the y-intercept, and those are all the points that are down here. And it looks like this. Everything right here. And my solution is that part that's being overlapped. Where they overlap each other. So this solid part of the absolute value, not the parabola, but then everything else inside is our solution. And now we have one more. And you can add as many as you need to these. So we have one more. Luckily, this is already isolated for us. So let me highlight this. We'll highlight this one, would be our red line. This would be blue. And because we already have the y isolated, our y-intercept is 0, 2. And our slope is 1 over 2. And that's going to give us a point here at 0, 2. Let me just move this graph a little bit more centered. It's going to give us the point here at 2. And then we're going to go up 1, right 2. And that's going to give us our second point. And since it's equal to, once again, we're going to make a solid line. We could extend this line even further. I sometimes forget to put the little arrows at the end. And now if you remember, this line was the one that we did a second ago, but I'll do it again really quickly. We subtract by 3x to both sides. That leaves us with negative 2y is smaller than negative 3x plus 6. I'm going to divide each term by negative 2. On the right side, I'm already splitting them. The 2 simplify. But when you divide by a negative, don't forget you have to switch your inequality. So that's going to leave us with 3 halves x minus 3. If you remember this one, it had a slope, the y-intercept at 0, negative 3, which is down here. We're going to go up 3 and right 2 for our slope. And this is going to be a dash line. Too thick. It's going to be a dash line right here. But I'm going to put it on the side so I can make all of the dots. And I forgot to say, for this problem, the shaded part, I already have the equal to the solid line, but the y, I'm looking for the ones that are smaller. So I go to my y-intercept for my red line, and the smaller ones are below. So I'm going to shade this portion here. And then this one wants the y values that are bigger than that line. So I go to my y-intercept. The ones that are bigger are above. So I'm going to shade that portion here. And the part that overlaps is in here in the middle. And this is the overlapping portion. trying to get it more uniform color. There you go. But that is our solution. This everything here, not the dotted part, but then everything inside is our solution. And that is how you do systems. I will next talk about writing linear equations.